So, hey guys, this is a new blog which I have written just yesterday and just recording a video to explain whatever I have done here. So it was a very unconventional idea or an unorthodox idea to use an encoder-based transformer model to actually generate language. So let's get started directly. So the title of the blog is Forcing a Bidirectional Encoder to Decode using BERT to generate language. So again, we will follow the same procedure that we have been doing uh, since the last blog. So I'll explain whatever the project is via the blog, and we will go back to the code to see some snippets to understand why they are there and how they are there. And we'll come back to the blog again and continue the flow. And let's see, I can actually make a live demo and show you how BERT can generate text when trained explicitly for a generation task. So let's get started. So as you all know, if you have been in this domain, the NLP domain or the LLM domain, you might already know that BERT or any encoder-based transformer models are really great at understanding the text and classifying them, or let's say whether two sentences are similar or not. So any classification task which doesn't require the model to actually explicitly generate more than one result, right? In that cases, BERT is really great. But when you want to generate more than one results or more than one tokens, let's say you want to you want to create a chatbot. So given a question, it generates the answer token by token for you, or any LLM for that matter, which we use nowadays, like Gemini, Claude, or ChatGPT, right? These are generative models, so they generate text whenever the input is given to them. So that is the golden rule which was being followed. So BERT is for understanding, GPT is for generation. Even the original transformer paper also had the same understanding. The original paper had the task of neural translation, so translating one language to another. So the encoder in that paper was explicitly to understand the input language or to understand the input sentence. And post that, the decoder used to pick up this enhanced or enriched uh, representation of the input language and take that as the reference and generate the tokens in another language or the target language. So that is how the original transformer paper was written. So now I asked a question to myself that what if we don't follow this rule? What if we can force a bidirectional encoder to actually generate data or generate language from its own? Like, of course, we'll have to train it, not use a pre-trained model. But can an encoder actually learn to decode as well? So the initial motivation for this project was really simple. Since BERT or any encoder model has access to all the tokens across the input sentence. So like let's say you are at token number 5, you can look all the way till token number 1 from when you see behind, and you can see all the tokens in the future as well till whatever sequence length that is. So since all the tokens are having the context of all the tokens surrounding them till the very extremes, this context can actually help generate the next token which follows the sentence in a better fashion or in a more fluent fashion, because we have more context here. So that was the motivation. Basically, its contextual accuracy should be richer than any GPT models, because GPT models are only forced to look behind. They cannot look ahead, and based on the context which they are carrying forward or the current token is carrying forward, only based on that context it is allowed to generate the next token. But BERT in that case can look at the whole sentence together, and then it can generate a new token based on whatever context it has developed. So I have developed this custom architecture, and I have used JAX as the framework here. So earlier in my earlier video and blog, I had used TensorFlow. So this blog and video, we will be exploring the JAX framework to code this architecture up and run all the training as well. So I had referred to two research papers from the domain, and one of them is it was published in 2019 from NYU and Facebook. The title says that BERT has a mouth and it must speak. So they proved that a pre-trained BERT can actually generate data because BERT model was trained on masked language prediction. So let's say you have a sentence. Let's say you have 10 token sentence and you mask, let's say, 3 tokens randomly in that sentence. BERT is explicitly asked to predict which is the most probable token, or which is the token when we put in here makes the most sense to predict those tokens basically. So let's say I give you a 10 token sentence and I mask out 3 tokens. BERT will actually put in the most valid tokens in their place. So what if you put this mask at the end? So let's say you have 10 tokens and the 11th token is what you mask, and BERT is asked to explicitly predict which token will follow this given context, right? And I think they have not explicitly trained in this, they have trained BERT in this paper, or I think they have given the comparisons of both pre-trained and custom trained model as well. So I think what they showed is it suffers from uh, a pit, like a pitfall, where it keeps on generating the same tokens again and again just because it thinks that it is safe to generate. I'll show you one example from their paper itself. Let's go down in the appendix and we will be able to see what I am saying. Right. So this is what they are saying, right? Random generations from BERT base using sequential left to right sampling strategy. So let's say you give this sentence, all people are good, no more, no less, and then you ask it to generate after a point. So what it does is it says dot 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 for dot 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 for dot 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 for multiple times till it starts making sense again. So this is kind of nonsensical, right? You just say for once and you generate the next tokens. So what is happening here is BERT is trying to minimize the error or minimize the mathematical error basically from it is not reducing the error from a human's perspective, it is reducing the error from a mathematical perspective. So what it is doing is since it has generated or since it has consumed some tokens, it will generate the token which is most probable after this given context. But what happens is when the new context comes up, so for this new context, what is the most probable token that BERT would generate? It will choose the most mathematically safe token which can be put up next to the given context. So in that safe zone, the same token gets repeated multiple amount of times just so that BERT can feel safe about its generation. It doesn't want to get anything wrong here. So just because it doesn't want to get anything wrong, it falls in this trap of generating the same token again and again, and it doesn't make sense for us humans to read this text, right? So that is what this paper had proved. Then there is one more recent paper which says that encoder-only models, or for example, BERT-based models, or BERT is an encoder-based model. So in those models can learn specific tasks or specific scenarios which cannot be learned by a decoder-based model. So I'll come to that task in a while, but basically, let's say for mathematical tasks, you have to look back and look ahead. So let's say when you are given a sequence of numbers and you want to choose some numbers based on some condition, let's say you are given 10 numbers. So up till fifth number, you generate some representations of the tokens which we have seen before, and the next token comes up. Now this token can affect whatever you have seen before. So ideally, in a mathematical scenario, you should use this information which you have seen just now to update the states of the previous tokens which you have seen, or the previous information should be updated based on the current information. This, however, is not really present in decoder-only models because they are only permitted to create the state once, cache it, and then just keep going ahead. right? But in case of encoder based models, whenever you see a new token, that new token can affect the states of the previous tokens as well. So that is what gives encoders more expressive power, right? So we'll come to the actual task in some time. So let's actually dive into whatever we have done here. So I have split this blog, or with respect to blog, even the video will be split up into three sections. One is the architecture, math and code. Then there were some hardware blockers which I faced, and I had to resolve them to achieve this task in a uh, let's say a limited time, right? Otherwise, given unlimited time, it is possible, but given a valid time step, or given a valid amount of time, this model has to converge. Otherwise, there is no point of this project. Then why this is a great learning project, but it is absolutely brutal when you want to train this model and actually infer from the model. So why this happens is because of KV caching, which we'll be covering later as well. There is no caching mechanism in encoder-based models whenever you want to generate data from these models. So that also we will cover in the future. So now what happens? What happens is with the last video or the last project, uh, I had actually built the setup on a GCP instance, and I had to continuously monitor it, logging in into that instance, then putting it, making sure to put it up, put the session up on tmux, so that I don't lose the progress if I accidentally shut it down. And of course, it was very pricey because I had to pay a lot of money to get to that instance and have the development done. So what I did was I was like, since this is a small model, BERT is not exactly small, but it is smaller when compared to the other models. And since it was custom built, I could actually tweak the parameters around to make the model fit into my laptop's VRAM. So I have the whole setup done on my system itself. So these are the system specs. It is TUF Gaming FX 505DT. Then I have a Ryzen 5. Then I have a GTX 1650 with 4 GB VRAM. And I have a RAM of 32 GB. So I actually set up all my environments on this GPU itself, and I was able to train the model and infer out of it as well. So I am using Docker on. So I'm on Windows 11 basically. So my host machine's operating system is Windows 11. So I've set up Docker desktop on this, and with that Docker I create containers which have CUDA already installed in that image itself, and I use Conda to create multiple environments to actually use TensorFlow vGPU as well. We can use PyTorch as well, and in the current setup, I have used JAX plus GPU support. Now, earlier it was a nightmare to install CUDA and cuDNN with the underlying CUDA version matching, and that CUDA had to be supported on these cards. And again, installing it on Ubuntu was a bigger nightmare because somehow it felt really hectic to do. But all of these frameworks have lessened that workload because now they have CUDA bundled in their wheel files itself. So you would usually have to do just pip install the framework, like the framework name, and in brackets if you give CUDA or the CUDA version. In here I have given CUDA 30. Automatically the related binaries and related binaries get installed. The only prerequisite that is required when you install this is you should have the CUDA drivers underlying installed in that environment. Right, so just doing this will give you everything that you require in this environment. So why I explored JAX in this project was because I use Gemini heavily for all my personal projects, and Gemini was trained using JAX. So I just wanted to see how JAX is different from TensorFlow or PyTorch, and just wanted to have a new framework in my skill set so that uh, I have all the three popular frameworks at my fingertips in just to say. So, however, since I was new to JAX, most of the API support or the API documentation or which APIs to use in what scenario and in which API will be optimal was uh, suggested by Gemini itself in our conversations about this project. So this project is basically exploring the theoretical question about whether we can use BERT for language generation and also about my exploration with JAX. So this block can have a mix of both. So let's dive into what we have here. So architecture is pretty straightforward. So I have created an encoder layer here, and the syntax of JAX is pretty similar to PyTorch in the way they have hierarchically arranged all of the classes and functions to be accessed. So I am using multi-head attention, the inbuilt multi-headed attention from NNX. So NNX is basically a JAX-based neural network library. So from NNX, I'm using the inbuilt multi-head attention. And then we have two linears. Basically, this forms the MLP block after the attention layer. And I am using Swish as the intermediate activation in this MLP block. So now what we do is we pass the input via a layer norm. So this is a pre-norm architecture. The original BERT architecture was a post-norm architecture where you would actually normalize this summation output. But what happens is when you do that, the backflow of gradients kind of is hindered. So it is actually a different topic, and it's an in-depth topic, and it would require a blog of its own. But just take me here for granted as of now that this works. This actually effectively works. So this is a pre-norm architecture which we have here. So you normalize the input first, then you pass it through the attention, and here as you can see it is all self-attention. So this is like the quadratic attention module where each and every token attends to each and every token. So the query key value tensors are all same. Then you pass the mask also to, so here the mask plays the role of telling the attention where there are padding tokens and where there are valid tokens. Then you add the attention with the original input, and then you again pass it through one more normalization layer. And basically, this is the MLP block where you do linear transformation, then you apply swish on it, and then you do one more linear transformation, and then you finally add it again and return back. One key thing to observe here is that if you are wondering why we are blowing up the dimension of the embedding dimension to 4x the original, that is because that has been the standard architecture which has been followed in BERT and GPT. So this expansion actually serves the purpose of working as a memory bank or working as the memory of the model. Here what happens is whenever you expand the dimensionality, the model has a lot more numbers to play with, and some problems can only be solved when you actually project it to a higher dimension, right? So these two combined will give you a better effect of actually memorizing or understanding what is being passed to it, and also solving problems in a higher dimension because they're easier to solve in a higher dimension. So that is one nuance. And also, as I mentioned before, I have swapped the post-norm architecture with the pre-norm architecture, and I'm using swish activation instead of GELU, which was used in the original implementation of BERT. So now coming to BERT backbone, this encoder layer is repeated n number of times in this BERT backbone, and you can see that here this forms the heart of the BERT model where majority of the learning happens, right? So one more interesting thing here to note is that BERT was actually trained with the positional encodings which are actually trained with the data itself, not the positional encodings which can be derived mathematically. So you might be aware of positional encodings which are sinusoidal in nature, and given embedding dimension and the position in the sentence, you can actually derive the positional embedding which can be added to the token embedding to let the model know which position the token is. But here, what I'm doing is I'm just using one more embedding table, which has the maximum rows to be the max sequence length, and the columns will be the embedding dimension. So even the original BERT paper also had the same implementation, where it is actually using learned position embeddings instead of a mathematically derived position embedding. The reason to do is because this is not adding much to the training as such, because this is a very small trainable parameter when you actually compare to all of these layers. And having a embedding which is trained on the data itself, and that which is representing position, is actually nice to have, so that you don't do a lot of complex mathematical derivations to just arrive at the vector representing the position. Let the model itself figure out what needs to be done with this position. That is what we are trying to tell here, right? So now that model, so this BERT backbone is being used in this BERT for causal LM. So now I have tried to keep the class names and the function names closer to Hugging Face uh, as much as possible, so that it kind of is relatable, and also the structure which Hugging Face follows is really good in a way that it helps maintain the structure of all the classes and modules which you are using in the current execution. So I have tried to use that structure itself. So BERT for causal LM uses BERT backbone as its backbone model, and then there is one more projection layer which kind of projects the embedding dimension back to the vocabulary size. So I've kept the vocabulary size as it is, which was present in the original BERT model, which is 30,522. So this outproj actually serves the purpose of a language modeling head. So what happens here is, whatever tokens you get from the BERT backbone, you can pass it through this outproj and actually predict which token it represents in the human understandable form from the machine understandable form of that vector. The 768 dimensional vector will be translated to one token which represents one human readable token, right? So now here in JAX, the actual model call is given by underscore underscore call. I think it is same in TensorFlow as well, but in PyTorch, I think it is forward. So those are some differences here. Then let now mask here again is representing which tokens are valid and which tokens are padding tokens. So here the mask is kind of expanded to 4D, because the attention actually happens in 4D, because the first dimension is batch. Second dimension, I think, is the head. Third dimension is the sequence length, and fourth dimension is the embedding thing. I might have switched I might have switched the sequence length and the head dimension, but it is basically 4D attention, right? There is one more thing which is interesting here, which is this last token indices. So now, since I want to fit this entire training setup on my 4 GB VRAM GPU, I have actually reduced the trainable sequence length to 64 from 512. So 512 was the original sequence length which they trained the BERT model on. But I have reduced it to 64 because I found 64 to be a sweet spot which I can train on my GPU itself. So this last token indices represents which is the last valid token in the current given sequence. I think I have a picture also for that. Let me just show you that here. Right. So let's say it is always going to be a 64 dimensional, 64 length sentence. And the fifth token is the last valid token. And after that, all are padding tokens. So the jnp.sum -1 is what gives us the ID of the last valid token. So we will see how we are using that. So yeah, that also you can see here how it is represented in Hugging Face data sets. So here if you see, let's say I have the sentence as Dormammu, I have come to bargain. So what that is represented as is these are the valid set of tokens, and after that everything is zeros, and this length is 64. So here this is the attention mask where all the ones represent the valid tokens and all the zeros represent that they are padding tokens. So that is what we have in here. That is what we are doing here. Then we pass this inputs to the BERT backbone, which we earlier saw. Then batch indices is basically how much, what is the batch size that you are passing, and we are just getting it from this, basically the zero shape of X. Then the last token in all the batches is taken and concatenated. So batch indices, so basically indexing in all the frameworks is same because underlying they use NumPy itself. So batch indices, then last token indices, which are coming from here, and the whole embedding dimension, which is 768. And that those last indices are actually passed to the language modeling head, which is the outproj. And this outproj again maps it to the actual vocabulary dimension to predict one token out of 30,522. So there is a generate function as well, which we will look at it in a live action. So what is happening here is we are accepting the current context, and the maximum sequence length is 64 here. That is so that it acts like a sliding window. So you predict 64 length sentences, and let's say you want to predict the 65th or the 66th token, you move that attention window to take the context from the second token till the 64th or 65th token to predict the 66th token. So it's basically like a sliding window, and the attention span is maximum sequence length, which is 64 in this case. So you pass it through the model and you get the logits, which the logits represent which tokens are highly likely to form the next token. So we are scaling it using temperature. So we will see why we are doing that. And then we are predicting a random token which has a high probability of coming up. So we are not choosing a token with the highest probability. We are choosing the token from a subset of tokens which have a high probability of coming up as a next token. We will see why this is also happening here instead of choosing the highest probability token. So we will see why that is not really helpful. So this is the generate function. Now this is the function that we use for training. So as I already mentioned, the dimension of the token is 768, which is similar to the BERT base implementation of the original paper, and the vocabulary dimension is 30,522. Right. So I think we looked at the call function as well, where I'm suggesting that why this 0 is required. So basically what happens is the 0 in the mask translates to a negative infinity value in the softmax of the attention, and since negative infinity goes through softmax, it becomes 0 again. 0 meaning this token has no information, please ignore it. So that is what is happening here. And I told you why we are doing this as well, since we want to get the last valid token, which will be passed on to the attention or the language modeling head to predict which token comes next. Before this, actually, there was one interesting experiment that I had done where we actually pool all the 64 tokens which are the output. So basically what happens here is in the model, so this X is basically batch size 64, the maximum sequence length, and then there is 768. So what I was trying to do is, I was like, why to waste any output that is coming from the model? Let's use all the tokens which the model is giving the output as, and let's pool them together. Let the model figure out of 64 which is the most important token it wants to use to predict the next token or predict the next most probable token. But that actually backfired. Why? Because since you are explicitly mentioning with the mask that from this token, all the tokens after this are basically useless. Attention really does not care about all of these tokens. So there is no much information present in these tokens that you can use to predict the next token. Actually, if you use it, you are worsening the training because the model cannot really figure out what is noise and what is actual uh, training input that you're providing, or what is the actual information that it has to use. So let's say you have a sequence length of 64, out of which there are only 10 tokens which are actual information, and the other 54 are padding. So now, first time the model sees this, it understands that, oh, okay, fine. There are 10 tokens with which I have to predict the next upcoming token, and the other 54 tokens are basically useless. So I will update my parameters to accept only the 10 tokens that are being used, and the other 54 tokens can be ignored. But now let's say in the next batch, you see a batch which has 12 tokens as information tokens, and the other 52 tokens are useless. Now, since the model was already trained to understand that only first 10 tokens are valid, it has to update its understanding that, oh, okay, fine, I am seeing two more tokens which are actual information, so I have to train using 12 information tokens instead of 10. So across millions of batches, this kind of creates a chaos, and the model cannot really figure out which is the maximum length or which is the minimum length till which it has to see and predict the next token. So this actually kind of failed really badly, and the loss value was not converging. It was hovering around one value itself, and it was not really going down from there. So the model was not learning. This was a good exploration to understand that not always all the tokens are important, and you'll have to give up some information to actually make things work, right? So that is what is happening here. And one more thing is that since I'm using a softmax here, you would see softmax here. Uh, Softmax actually forces the model to play a game where you have to always sum the probabilities to one, or always sum the weights to one. This boundary, or this constraint, actually ruins the training of the model as well. That is what I have observed. So I had to give up this approach, and I had to actually fall back to using the last token as we are doing here. So we understand which is the last token, and we actually pass that token to the language modeling head and ask it to learn from the last valid token. So that is what is being done here. So I've just put up some memes so that it becomes interesting for reading, and it is not a very text-heavy blog. So now here I have used Gemini extensively to understand how BERT works, or how the training in JAX can be set up efficiently. So this last token, usage of last token, was actually suggested by Gemini itself. And when I asked the reason of why only the last token, why can't we pool everything, and why is pooling causing a problem, it explained why pooling was causing a problem. But interestingly, why we choose the last token only, or I think we can independently choose any of the valid tokens, because by the time the information comes up till the last token, each and every token will have the context of each and every other token, because the attention is by architecture allowed to look at each and every token in a quadratic time frame, right? So first token can look at second, third, fourth, all the way, then second can look at first again, and all the way. So by the time it comes to the last layer, each and every token has the context of each and every other token that can be used to predict the next token. But since we want to predict the very next token, the last token kind of makes more sense from an intuition perspective, and also from the ease of coding perspective, right? So you just extract the last token and you pass it on to the language modeling head. Now, there was one more problem. Now, since I'm using 64 length sentences, we cannot always make sure that the production environment will always have 64 length sentences itself. Sentences can be of 3, 4, or 5 tokens also. So the model needs to understand that sentences can end way before it hits the 64 length mark. Now, why this is important is because we are not using mathematical positional encodings to tell the model where the position is. The positional encodings are also being learned based on what data it sees during the training. So we actually have to model this scenario where the model is actually trained to understand shorter sequences as well, the total 64 length sequences as well, and anywhere in between. So that is why I had designed this dynamic batch generator, where given one sentence or one example, it kind of randomly chunks the given sentence at any position given. So here I'm using this np.random.rand int. So from first position till the context length, like the 64 length, it can cut down the sentence anywhere. And from that position, everything will be padded, or everything will be a padding token. And before that, everything will be a valid token. And the target token, which the model needs to predict, is the token which is right next to the valid token, right? So now the model now kind of understands the, okay, I have a sequence length 10 and I have to predict the 11th token. Then in the next batch, it will see, okay, I have a sequence length of 20, I have to predict the 21st token. So on 25th, 25 positions are given, 26th token has to be predicted. So that is what is happening in this dynamic batch generator, where we are masking the sentence after certain position, and that basically the target which the model has to predict is the very next token after the last valid token, right? So that is what is being done here. Now, why we are doing that, there is one more reason. Any GPT based model or any standard decoder based models, they have more information while they are training. What happens is they use a lower triangular causal attention mask. It can be lower or upper triangular based on how you represent valid or invalid tokens. But it is a triangular matrix which kind of tells the model it has to look only behind, it cannot look ahead. So simultaneously, whenever you're giving a 64 length sentence to the model, it understands that, okay, I'm at the first position, I cannot look back, so I have to just consume. Then it predicts the second token. So in the same forward pass, it sees the next token as well. So when it sees the next token, it understands that, okay, I have seen the first token, I've seen the second token, I have to predict the third token. So this goes on in the same batch. It can predict 64 new tokens based on the input given to it, because it is a triangular mask and it cannot look. It can only look behind and it cannot look ahead. So whenever the gradient is passed on to this GPT model, that is a very dense and very information-rich gradient, because it has predicted 64 uh, 64 words by just looking at one input sentence. BERT does not have this flexibility because it is a bidirectional model. And since it is a bidirectional model, there is information leak as well. So because it is allowed to look behind, it is allowed to look ahead as well. So it can't really mask out the future tokens just to predict the next token, right? Because that next token is already answered because it can look ahead. So that is why we have to kind of dynamically simulate this scenario where BERT model is forced to learn all the positions given one input sentence. So the input sentence is 64 length. You chop it off at any valid context length. The context becomes the chopped up length, and the target becomes the very next token, which is appearing after the last valid token, right? So that is what is happening here. And the other parameters of the model, the training pipeline are here. Basically, there are every batch has 5,000 samples, and every validation batch has 500 samples. And I'm using a cosine decay schedule because that is what is generally recommended for any attention-based models. Because if you don't linearly scale up the learning parameter and then decay it, the transformer models are initially shocked when they receive a very large gradient, and that kind of ruins the training process. That is a different concept, and it requires again a different blog of its own. But let's just take it for granted that we have to use cosine decay rule or any decay schedule for the learning rate, and that learning rate is being used in here. And so there is one more JAX based library, I think, called Octax, which allows us to chain whatever we want to do on the optimizer. So basically, I am clipping the I'm clipping the gradients and making sure that they have a norm of 1, so that there is no overshoot of the model parameters because the gradient is too high. And then there is I'm using Adam W optimizer with the learning rate of this warm up cosine decay schedule with these parameters. Then there is this loss function. So loss function is basically the same softmax cross entropy with integer labels, because we already have integers. We don't have to map. There is no mapping required here again. Then there is this train step. Here I'm using this nnx.jit. So what this does is, given a whole model, it tries to compress all the functions that are happening in the model in one single GPU kernel of sorts, and that whole GPU kernel is put on the VRAM of GPU, and the model updates and the forward passes, backward passes are all done using that kernel. And same is with the validation. The same, it tries to kind of compress the whole model into one kernel and do a forward pass on that. So that is the training pipeline. Coming to the most major kind of part of this blog is the challenge which I faced when I wanted to fit this whole thing on a 4 GB VRAM. So what happens is, whenever you're training a model, since this is a laptop, this is not a server, I wanted to stop the training sometimes because I wanted to game for some time, and maybe I wanted to do something else which required the GPU, right? Because this, whenever you run models with GPU support, the GPU is basically occupied for the whole time the training runs, right? So you can't really use the GPU for any other thing. So here, one concern was, let's say I don't want to do gaming, or that's a different concern. Lights go away and the laptop just shuts down. What happens in that case? There is, you might be already aware that models can be saved, but just saving the models doesn't really help, because the optimizer state also needs to be saved, and that is a very tricky thing to do. Now, why you have to save the optimizer state as well? Because the optimizer has learned to adjust its parameters and tune its parameters according to whatever data it has seen till now, and it kind of tries to smoothen out the gradients from that point. So till this point, it has learned how to kind of smoothen till now, and it will use this information to smoothen the gradients further. But now that smooth gradients also kind of help the model to update its parameters in a smarter way, or in a nicer way. But whenever you have learned weights, but your optimizer starts again from scratch, that optimizer will generate a gradient that will shock these parameters, and the model will just go into panic mode and lose all of its, not all of its, but majority of its learned things, right? Because you're starting again with a massive gradient that comes in and tells the model to upgrade itself or update itself in a massive way. So that is better to be avoided, and that can be avoided using checkpointing. So JAX provides us a way to checkpoint the model weights at that given point and the optimizer state also at that given point. And you can load these back whenever you start the training again from scratch, once you have done gaming or once you have done using the GPU for whatever task you want to do. So what we can do here is, there is one more library which is called, let me show you that library also. I mean, I call it OCP, but I don't know what OCP is. Okay, it's called Orbach's checkpoint. So OCP gives you a checkpoint manager which kind of stores the latest three values here. So this three can change. So I have kept it three. So it stores the latest three optimizer and model weight states, and you can kind of load these back. So Orbax takes care that it will always load the latest one. So let's say you have 1, 2, 3. It will look at your directory, and it will see that, oh, 3 is the latest. Let me load that 3 into the current state of into the current running session. So that is what is happening here. But the problem here right now is you have two two sets of model weights which are in currently in VRAM. One is what happens is you have something, let's say you have water in this container and you have to pour it somewhere. But to pour it also you need one more container, right? So that is when you pour the water in this container. So what happens is currently in the VRAM, this model instance has random weights. This is not a learned model, and it has random initialized weights. And this learned weights has have to be copied into this model, and this model will start training with the learned weight at whatever step you have stored. Now, this goes forward into training, but these weights are still on VRAM. So VRAM is having two models at the same time uh, with only one being there. It makes sense, right? So you have only this and you'll have to delete this. But I wasn't doing that. So because of that, what happened is since VRAM was full with these two itself, whenever I try to train the model by loading a new batch, that batch, whenever it tried to occupy some space in the VRAM was not available for it at all. So it used to crash in an OOM error. OOM means out of memory error, because it is not able to occupy space on VRAM and then train the model, right? So now that is why what we are doing here is we are deleting the restored states explicitly and asking Python's garbage collector to collect this data and remove it from VRAM basically. Now doing this, by doing this, you only have one instance of a model on the VRAM, and whatever number of batches you can fit into VRAM, those can be fit, and the model training continues. So this is a very important step when you are when you're doing training on very constrained bound environments, right? You just have 4 GB and you don't have fleets and fleets of GPUs to train your model on. You just have a very small GPU. Compute is there, but it's just that you don't have enough space to keep your items or artifacts in the VRAM. You have to take these drastic steps. And the problem here is Python's garbage collector is kind of lazy. Whenever it sees, like whenever it is neck deep in the water only, then it starts to try to swim, right? So unless you explicitly tell it to collect the garbage, it won't collect. So you'll have to tell it here. So that is what is happening here. One more thing which you'll have to take care is, like, since your stock is like let's say you have 100 samples in certain order. You have 1, 2, 3, 4, all the samples arranged in 100 samples arranged in one order. You stop the training at, let's say, 20th sample. You do gaming and you come back and again you start. But the problem here is the same sample one will be shown again to the model, and how many times you stop this training, that many times it will see the sample one again and again and again, and it will try to update its weights or its parameters to make sure that it gets the sample one correctly classified. This is actually wrong because it will overfit the first n number of samples itself. So you'll have to always try to shuffle this data set whenever you try to load this data set. So that is what we are doing here. So Hugging Face dataset gives you one API called shuffle. So every time you try to load the dataset, it will start from a random point using this seed as the reference, or this seed to compute where it should start, right? So these two things have to be this thing also has to be taken care, because we don't want the model to overfit on any of the stories or any of the samples that it should see. Right, so that is what we saw here. The VRAM double booking is where you have two instances of the same model and you try to load something else on the VRAM and it just errors out, right? So that is one thing. Then there is one more problem which I face is now this is not a one device game. Training is not a one device game because CPU and RAM will always orchestrate the data from your disks to the GPU. So now what happens is whenever it is trying to pick up some samples from the disk, they are intermediately stored in or they are stored in the RAM for some time before passing it on to the GPU. Now, when the CPU or the RAM starts bloating up, CPU kind of panics because it is not able to find what it requires immediately, and the GPU becomes starved of data because CPU is just trying to put the next valid set of samples in the GPU, right? So now, what happens because of this? Since the RAM is getting bloated, we'll have to clear the garbage in the RAM also. So now that is what is being done here as well, right? So there are some things which are okay. I think I have not put the code for that here, but I'll show you the code of that training as well. So whenever I was training the model, I made sure that whatever artifacts were loaded, let's say these batch inputs, batch masks and batch labels. So these are valid only for one batch, right? You don't need them in the next batch. So I was explicitly deleting it here and asking Python to clear the garbage in the RAM also. So with this, what happens is the RAM stays clean and CPU does not really have to hunt for places where it can put the next valid batches for some time in RAM, and then from RAM it has to put it to VRAM. So since the RAM kind of is clean right now, CPU can kind of work fast, and the GPU does not get starved of data also. Now, after this, after battling all of these hardware demons, I was finally able to train the model, and I trained it for a significant amount of time. So I think I trained it for almost 15 days continuously without shutting down my laptop. So it was on for 24 hours, all the 15 days. So then now since the model is trained and the loss values are also decreasing, I tried to actually test it out for what it is being trained. So I wrote a simple inference script here, which is telling the model to accept whatever is the current context. Then it is taking the next token based on, it is doing a argmax here. So argmax basically means, let's say you have a set of tokens and one has the highest probability of occurring as the next valid token, it picks up that. And you take that, you concatenate it with the previous given context, and in attention mask you say, okay, this is the next valid token. So put a 1 there instead of a 0, and this loop repeats till max number of tokens. But what happened? So this was the input sentence. The little dog ran into the park and saw. The model completed it with this: big furry dog. The dog was very friendly and wagged its tail. The dog wagged its tail and licked their faces. The dog wagged its tail and licked their faces. The dog licked their faces and wagged his tail. So basically, you can see that the generated sentences are kind of repeating in phrases, right? So this is again a mathematical trap where the model tries to be as safe as possible whenever it is predicting new tokens, because it is trained to make a safe prediction, right? Given this context, what is the next most probable token that appears sensible, or sensible in human language, mathematically safe, or mathematically optimal in the BERT's language? So why this happens is because you're doing a argmax without thinking, right? So to take care of that, I introduced the concept of temperature. So what temperature does is basically this. So this is temperature one, where these are the orange dots are the softmax values, and after dividing it by temperature, you get a different distribution kind of thing where the values are a little different before applying the temperature scaling. So with temperature scaling, what happens is you basically are trying to maximize the occurrence of certain tokens. So let's say there were 10 options, and out of the 10 options, 5 had the probability of occurring more. Of course, among these 5 tokens, one will have the highest, but these 5 will have some higher probability than the other 5. You are scaling up these probabilities a little bit more, and then you are doing a random categorical on this set of tokens. So what happens is, instead of choosing the highest probability token, now you have 5 options, and out of these 5 options, you choose the one which kind of is closer, not the closest, but the closer, but a closer candidate to given this context, which is the next closer candidate which can appear in the which can appear as the next token to make the sentence more sensible. So that is what is happening here. So after that, that is it generated the valid tokens which were sensible to human as well. So after these changes, you can see here, this was the same input sentence. The little dog ran into the park and saw a new friend. He was happy and held the dog outside. The dog looked friendly and they played together. The cat and dog were best friends. They played together every day. It was a good day. The dog liked to play with the ball. Now here, though there is a disconnect between the consequent sentences, it does make sense. I mean, if a human is reading, they will get the context and understand, okay, it is trying to make something out of something which was given as a context, right? So I would term this as a success because it is trying to generate coherent sentences, and it kind of is successful in doing that to some extent. And it is actually better than just repeating something over and over again, right? So now we have whatever we wanted to do, but why this is kind of one of like the worst possible ways to generate language, right? Let's just have a look at that. Before that, I think there is a mistake in the blog. I had to put a section here. Let me edit that here itself. I had to put the marker here. Right. So let's go back there. Yeah. Now let's understand why this is very heavy on the GPUs or any device that you're running on, right? Now, GPT-like models have the permission to only look behind, and they cannot update those states based on the next token that they see. So basically, the previous tokens or the previous token states don't really change, and you can, since they're not changing and you will be reusing them going forward, you can basically cache them. So that KV cache is a massive optimization on massive optimization for these LLMs to generate text and on a use in a longer context length, right? Because you have already cached it, you don't really have to recompute anything. But that is not the case with BERT. BERT, what it does is, if you can see in the chip that I've attached here, every new token will affect all the previous tokens that it has already seen, and those token states, though they have more expressive power, they are changed. So since they are changing, you cannot really cache them in any way and use them again and again, right? So it becomes basically a O of n squared task with no optimizations whatsoever like caching, and you can bring it down to a manageable complexity. So if you try to predict, let's say, n number of tokens, the time complexity will go on increasing. So let's say n is basically the time to consume one token, and you have C tokens at the first. You consume that in n C square time, and in the next, since you have one new token which is generated, for the prediction of the second new token, you will have to go through n into C plus 1 the whole square time to predict the second token. and this time builds up. And this is extremely massive when you want to scale this model up to a level where it becomes a chatbot handling multiple queries at the same time, right? If you actually put this in production, the user will just have to stare at the screen to even get the first token, because the initial amount of compute is also massive, and the compute just keeps on becoming more and more massive every time you add a new token to it, right? So that is one major problem. One more problem is, it is not just inference that is the problem, it is also the training that is the problem. Because what you're trying to do is, you're trying to simulate the positional information also, which we discussed earlier. So as I mentioned before, since the standard GPT model uses a triangular causal mask, it has basically learned to predict the second token based on the first token, and sixth token based on the first five tokens, and 64 token based on the first 63 tokens. So here, GPT model have a massive advantage of extracting 64 times more information with just one sample, and that information is basically passed on back again to make good updates to the model. But this is not happening in case of BERT, because BERT has this data leakage problem where it can see the next token which is already present in the sample, right? So that gives BERT the disadvantage of basically looking in the future and not learning enough to predict that token itself, right? So for training as well, so let's say if you want to actually make it learn, you can slice the 64 token sentence into 64 different slices, where the input is first input is just the word, and then word 2 is predicted. Then the next batch will be word 1, word 2, and the word 3 will be predicted, and so on. But if you do this, it will translate the problem complexity from n squared to n cubed, because you're already computing the attention in n squared, and you are adding one more layer of n, just because you want to make sure that the model is trained on all the positions possible with that sequence. So just to, that is not possible. It is possible, but it will just take a lot of time, and it will basically, you'll have to keep your laptop running for an eternity, right? So that to just overcome that, I have designed that dynamic batch creator, which is kind of a stochastic causal simulation, where you predict or you chop off the valid sentence at any valid point, and then you predict the next token, which is the target becomes the very next token, where the last valid token is present. And since it is a uniform sampling, we are pretty confident that all the positions are evenly covered. So that is what happens with training. Now, after applying all of these tricks, I was finally able to train the model, and the model, I had trained it approximately for 54 lakh 65,000 steps, which kind of translates to, I think, 5.4 million steps. And this is the output of each and every. So I ran for 3 examples. So this is basically the completion. So the little dog ran into the park and saw a bright, lovely dog. They ran to them and barked happily. Peaceful, I don't know why they are here. They were so happy to be friends, and they were very friendly. It is kind of repeating the same thing in a contextual way, but it is not really repeating the same phrases again and again. So there is one more sentence here. Timmy was very happy. He found a big red. He found a big red apple tree. He said, "Thank you, Timmy. Thank you, friend, for helping me." From that day on, Timmy made sure. Again, it is contextually not correct, because he's saying thank you, Timmy, when he himself is Timmy. Or maybe there is one more Timmy which he's talking to, but you get the idea. Then there is one more sentence here. Once upon a time, there was a little girl named Lily. She loved to play with her. She loved to play with her toys, but her favorite thing to do, she loved to draw with a crayon, but she knew it was important to be careful with. This kind of makes sense a little bit. So now that was it for the training perspective and what are the disadvantages of actually using BERT for or any encoder-based model for generating the language, right? But is it always the case? That actually is no, because in this paper, the encoder-only next token prediction, the authors have introduced one task called as count three task. So what happens here is you are given a sequence of numbers and you have to predict or you have to generate pairs of numbers where every xi plus xj plus xn mod n should give 0. So that is the task. So if you see here what task they are trying to do or trying to make the models work with is given x and values, you have to give me the pairs of numbers where every xi added with xj added with the last number xn mod n gives you 0. Now, why would decoders not be successful here is you can even read the paper and understand that decoders are not allowed to update the token states which they have already seen because they want to cache it. But in case of BERT, every new token which it consumes updates each and every token representation or token state which it has already seen. So now let's say I see a xj number or xj number and I already have access to xn because I can see in the future. I have the information of xi's which combined with xj and xn will give me a mod of 0. So I can update the states of xi's which I've seen before xj and use that information to generate a new pair, right? So every time I see a new xj, I'll update the previous states, make sure that those updated states will be used in the next xj computation as well. So whenever you want to update the previous states, encoder-based models are the models you have to go to because decoder-based models don't have the permission to update the states which you have seen before, right? So that is what they have mentioned in this paper, encoder-only next token predictor, right? So that is what I have referred. Now that concludes this project as well. And if you want to have a look at the code base is open source here, and I have attached the link in the blog itself. If you want to actually run this model and check, you can clone the repository and follow the steps over there. Because the weights of the models were really large, I could not push them into GitHub. So I had to push them into a drive folder, and that drive is basically made public and you can clone the weights from there. And you just have to install Streamlit because that is what helps you run in a graphical manner. And you can just run this command, Streamlit run app.py, and it will give an interface like this. Here you can control the max tokens, the temperature, and whenever you give the prompt and hit generate text, you will see this text generated one token at a time. So you will actually see it being in a ChatGPT fashion where it generates one token at a time and it gives you a feel. But it takes a lot of time and you'll have to have patience with this because it is basically O of n squared calculation at each and every time step, right? So it will take a lot of time. So that is it for this video. I will try to update the repository if some more changes are required. And this blog is public. You can actually read it on Medium. So this is it for this project. I'll see you in the next one. Bye-bye.